All right, galaxies have grown, and we'll see some movies that will show you how they grow. They grow by their gravitational attraction to each other. What happens when two galaxies collide? Now, when we collide with Andromeda, it will turn out that probably not a single star will collide with another star, because the space between the stars is so large. Remember, the nearest star to us is measured like, it's several 100,000 times the size of our astronomical unit. That means that they'll just pass through each other and they'll never hit anything. So these are called collisionless. They're collisionless because nothing happens to them. This is collisionless dark matter, or collisionless objects. Okay, and quasars were more abundant in the past than at present. Quasars are these active galactic nuclei. Why were they so bright in the past, and now they're generally pretty cool? Quasars are the giant black holes at the center of galaxies. What happens to them? What happens? Well, we'll talk about that. Now, let me show you. This is visual. This is done by Frank Summers. He made this movie. Let's see. Okay. Now, this is a simulation of two galaxies that are attracting to each other. Blue is the outer portions. The galaxies first attract, then they collide, and they don't actually hit each other, but they collide and pull out streamers. The streamers come back, and they merge to form a bigger streamer. I mean, a central region has grown bigger. And if it had black holes, they will merge to form one black hole. Okay. Next, here's another simulation. This simulation is primarily gas. In the gas is, they also show an active galactic nuclei here that's going to blow up when it starts getting fed by gas. It falls down into the center of the object, and then it gets really angry. It starts spewing out all types of material. Here it's going to start now. Here it goes. The red objects are hot gas that it's expelling. The hot gas starts to expel the dust and gas. That's what this is. It makes a holy mess. Sweeps the galaxy of all gas and dust. And blam, blows out all the gas and dust. This is probably the mechanism that, whoa, ferocious. This is two black holes getting close together, and they, pretty neat. Okay, this has blown out all the gas in the galaxy, which is extended out a long way. And if there's no gas in the galaxy, then you don't form stars. If you don't form stars, the object becomes red. And we think that is what happens to elliptical galaxies, which are red. This was done by Volker Springel and Lars Hernquist. Volker Springel is a scientist at Max Planck Institute for Astrophysics in Germany. Lars Hernquist is a professor at Harvard. Okay, now look at this. This shows the formation of a galaxy. Here it is, 0.95095 years. So the galaxy is going to form it's going to form well in the past. Remember, the age of our universe is 13 billion years. So it'll be counting along here. The galaxy will form, and it's going to form, the whole coordinate system is, in all these simulations, the coordinate system is done in what is called co-moving coordinates. We've already seen that a little bit. All right, in co-moving coordinates, you have an object. Here it starts off, and then later it grows big. All right, this is thought of as the size of the universe. Now, what's going to happen is it's going to plot, everything is going to be in fixed units here. So the expansion of the universe is not shown. It'll plot everything in this coordinate system. And the coordinate system are simply expanded. But it's the same coordinate system. This is co-moving to go from here to here. Co-moving in a sense that here's a galaxy, here's another galaxy, and the galaxies, do I have the same? Yeah. The galaxies are here and here. So in this unit, these galaxies are closer together than those galaxies. But the whole system is, everybody in the simulation, there's knowledge of the expansion, but they don't show the expansion. So that makes it easier to see this. All right, let's turn this on. Okay, what happens is the little overdensity grows. The overdensity will become part of a galaxy. It's growing, and here comes another one, a collision. The filament structure is, you see this is getting denser. Here's 2 billion years. This is a little galaxy. It's going to have other collisions. Here's comes some more. And all these galaxies are flowing together. All this in co-moving coordinates. And the galaxies are swirling to make a real galaxy like our own. Here is an object that's swirling around, just like our galaxy. Very content, all attracting other stuff. Lots of little stuff around is falling in. And here, bang, that's a sizable collision. The collision at first, they don't really stop. They do a dance. See, they do pas-de-deux, and then they make a galaxy. Okay? And the galaxy later is simply sitting there and attracting the matter around it. That is how our galaxy formed. Our galaxy had a very, very violent youth. Lots and lots of collisions. Here we're only up to 9 billion years. What's plotted is fluffy particles. That's actually the gas around the galaxies, or pieces of galaxies. We're not showing the dark matter. Is that neat? Pretty neat. Okay. Now, all right, here's another one. This is, let's see if I can figure out how this one works. Okay, this is a universe expanding. It's attracting material. It's really violent. Now we see this this is at a redshift of order 10, and the universe was really different. The galaxies were in small pieces. Now this one shows these bubbles are the expansion of supernova remnants. When the supernova remnant occurs, it blows the gas away because the supernova has so much power, and it blows it away. Then the gas forms again, a big merger occurs. There's a merger, or there's a supernova. Here's more supernova, blows it up. And eventually it gets so large, it does have supernova in the center that form the black circles for a moment. Another one. Another one. This again is a gas. Another one. And eventually it settles down to a merger. And you formed the galaxy. Now those supernova remnants, as they blew up, are what is polluting the galaxy with heavy metals. And the heavy material, anything higher than helium, more or less gets made in supernovae. And that is necessary, of course, for our existence. We wouldn't be here without it. We are, after all, stardust. We're the results of violent explosions in the past. Astounding. Okay. Now, if you look at the galaxy distribution on larger scales, we're now past the galaxy scale. We're going to observe the universe on bigger scales. This was a very surprising episode. Now here, what we're plotting is the observer sitting right here, and we're looking out. Plotted here is the redshift in a simple way. Redshift is V is equal to h naught times d. All right, these are distances, and plotted are each point is a galaxy. Now the question is, why the hell are the galaxies distributed in this way? Now what this says, if you look at it closely, this is the Harvard stickman. This is my work. I did this work when I was at Harvard. Here's the stickman, here's his head, here's his feet, here's his arm. He's a skier, actually. Here's the long ski poles, see? And he's flailing around about to fall. Now, this data was collected basically 30 years ago when I was at Harvard, and it was crazy. We didn't expect anything like this. We thought the galaxies are distributed. They don't know anything. So this was a very big surprise. Why are the galaxy distribution so non-random? This is not a random distribution at all. Very big there are voids. There are large filamentary structures called great walls and voids all over the place. Why does it do this? All right. So why, of all this data, drove me to come to Berkeley? I didn't see how I could understand this. I didn't feel like taking more data. I came to Berkeley to do n-body simulations, and I'll show you some of them. Now, in the 30 years, people have done amazing studies. This was done on a 60-inch telescope. We built the instrumentation for it. Really crummy instrumentation compared to today. This survey is huge. This is out to 10,000 kilometers a second, and what is that, billion light years? It's only right in the foreground. This is a survey in the sky it's done on a big 4-meter telescope, and they were able to do about 50 or 100 galaxies at once. And I had to do my survey one at a time. Point, point, point. It took a while to do that. It was pretty laborious. Okay. Now on scales of 10 to the 8th light years, the galaxies are distributed in chains and sheets surrounding these giant voids, 10 to the 8th light years. But they're clumped together. Galaxies are rarely isolated. Normally they're in groups, clusters, superclusters. These names don't mean very much, just that the galaxies are grouped together. And the distribution is incredibly non-random and large filamentary shapes. All right. And this is a hierarchy of structure. What does it tell us? How do we know what it means? Okay, but if you go to bigger scales of, say, 10 to the 9th years, which is this much, bigger than this, the galaxies are evenly distributed. The filaments and voids are pretty even. The galaxies are the same everywhere. And that was the conjecture necessary to make the models that Einstein first talked about. He talked about a homogeneous universe. And this is hardly homogeneous, but if you average on long scale, if you have really lousy vision and you see only on big scales, then it's pretty homogeneous. And so that is okay. All right. Now, this is a simulation. This is a more recent simulation of structure formation in the universe. It looks exactly like the data. The data shows filaments, voids, exactly the same. How does this simulation work? Now, the simulation is doing the simulation with dark matter of a type known as cold dark matter. And this thing is incredibly like the data. Why does it look so similar? Now, I came to Berkeley to do these sort of simulations. We didn't have the computing power necessary. We had a VAX 11780. Anybody know it? Everybody ever heard of that machine? VAX 11780. I mean, it's older than you. And it was about as powerful, less powerful than one of the original laptops. 8086 processor in those, was that the name? Anybody computer savvy know what they're called? Really fairly primitive processor in the first laptops. But it was 30 years or 20 years for the field to change, for the computer industry to change enormously. And we always use the latest computers to do the type of work. And what we had at the beginning was totally a joke. But it was fun. We couldn't quite do anything this pretty. All right, now let's look at this model. Okay. Oops. What happened? Hey, that's not supposed to happen. Oh, okay. All right, here is formation of a galaxy. This is again in co-moving coordinates. The galaxy, actually this is not co-moving coordinates. This is physical coordinates. And the galaxy forms. Didn't I show you this? Yeah, I don't want to see this. Okay, let's skip this. Here's another simulation, this one by Ben Moore, who was a postdoc here. Here is the size of the universe. Oops. Okay, the size of the universe starts off at 0.09. That is about redshift about 11 or so. Okay, so if we play this one, this is now in physical coordinates. That there is the redshift. The structures are forming. They're all forming because of the little fluctuations that were in the original universe. They form. They form. See all the clouds around it? Okay, and that is supposed to be a picture of maybe us and Andromeda. This might be what we look like. Here's us, and here's Andromeda, with lots of junk between us. That might be what it is. Okay, now how do you measure the mass? We want to know what the mass of the cluster will be. We see this in the sky, so how do we know how heavy it is? In a cluster of galaxies, the orbits don't happen in a time scale you can look at. They may be buzzing around like bees, but if you take a snapshot, it's it. You don't get to see it again. But what you can do is nothing moving. In spite of this, you can still estimate it because you use the same trusty equation for circular velocity. V squared equals gm over r. This equation we've seen again and again. So what do you put in? You measure r and you measure v squared. And how do we do that? Here, for example, we want to measure the mass of this cluster. It has two bright galaxies here, and all these little things, little red things, are galaxies that belong to it. All right. This is the Coma cluster, and Fritz Zwicky was the first to discuss it 50 years ago. And now this thing has a size on the sky of about 1 degree. The recession velocity you can measure from the spectral shift of this is 6,900 kilometers a second. All right, so you put it together. Hubble's law. H naught d, theta, the velocity is 6,900 kilometers a second, and this tells us the distance, the size of this thing is H naught equals 70, and the diameter of this whole cluster is 100 megaparsecs. All right, that's just from applying Hubble's law. And by a small angle approximation, using a small angle for the object, the theta times the distance is the transverse size. And that means that r is 2 megaparsecs. So the size of this to here is 2 megaparsec. That tells you basically how big the cluster is. Okay, this is Fritz Zwicky. He was a fairly ferocious character. These are some books that he wrote. It's somewhat crazy, but there's Fritz, good old Fritz. You get some really ornery people who go into astronomy. He was definitely a character. Okay, so you measure the mass. Now, what you can do is you look at the velocities. There's about 1,000 galaxies in the cluster, and you see the velocities are moving relative to each other at about 1,000 kilometers a second. And so you say that's the velocity of the cluster. Okay, 1,000 kilometers a second, that's pretty serious. Remember that our velocity around our galaxy is 200 kilometers a second. This is very high velocity. All right, and then you solve for the mass. V squared r over g, and that turns out to be 4 × 10 to the 14th times the mass of the sun. What does that number mean? Now you can add up the light of the galaxies, and you find that you find a number that's 50 times. This is 50 times more than you get by adding the starlight from the cluster and assuming a certain mass per star. So the power of this tells you right away that this galaxy cluster is not dominated by ordinary matter. It is dominated by something we call dark matter. The Coma cluster is dominated by dark matter. All right? This is one example. If you study other clusters, you see exactly the same thing. Oh, and the question is, what is this mysterious dark matter? What in the world can it be? We want to understand it. All right, and here's various ways you can understand it. If you have a cluster back here, and you're trying to take an image, here you look at it, and a real galaxy has, because it's a curved space, you know, the light is bent on a curved space. The light will come this way is bent, come this way is bent. Here it is. Here is the same object. This is the same object bent. You see it in 2 views there. You see it in more views here. That is one galaxy. that you see in multiple times. This tells us, now the bending of this thing depends on the mass. It doesn't depend on anything else. You know, that's what determines the bending that determines the depth of the potential well, the mass of the object. If the mass is baryonic, ordinary material like our galaxy, you get an answer. But if you put it in a lot of dark matter, the dark matter may not have light, but it has mass. And this is a way to measure the mass of the dark matter. A lot of mass in that. Okay, look at this one. This is so incredible. This is taken with the Hubble. Here, look at this arc. These arcs all over the place. Here's an arc to there. This is measuring the mass of these two. Here's arcs. This is incredible. This was a great surprise when these were first seen in the 60s? No, late 70s, when the pictures got good enough to see this. This is totally amazing. But with this, known as strong lensing, you're able to measure the mass of that galaxy cluster. And it's pretty damn neat. Here's another case. This case has blown away the entire community. Now, you saw some of those simulations where the galaxies went right through each other and then turned around. Now, if they go through each other, what's going to happen? This in the blue is a measure of the dark matter as measured by the lensing of the material behind it. So this guy has dark matter here and dark matter here. The red image is what you see when you look at the galaxy in X-rays. Now the X-rays are made by ordinary material, baryonic gas. The X-rays are formed when the gas collides or gets bent by another particle. It's moving fast and it emits an X-ray. This emission, what has happened is these two dark matter dominated objects have collided. But the gas in them gets stripped out by the collision. The gas cannot go through each other. If you take a gas cloud and hit it to another gas cloud, it'll collide. It's not like stars. The gas is microscopic, it collides. And the gas cannot go through the other thing, and it's left behind. This one's like a bullet. That means it's formed a supersonic jet. It's a blast wave going through it. So here's an object. This is amazing. This object is a cluster that is forming and has been through once, and in that passage, the gas is stripped out of it. Now, what it says is the following. First of all, the dark matter did not suffer these collisions. The dark matter is therefore collisionless. All right? The dark matter is not like ordinary matter. Ordinary matter would have suffered collisions at that point, but dark matter does not. Why? Why doesn't it? And the answer is it's known as we think it's a weakly interacting material. And I'll talk about what that means in a moment. All right, so the dark matter has really, in this case, collided and made a beautiful demonstration, because the dark matter is collisionless. An amazing photograph. Now, here I'm going to next show you a gravitational lens. A gravitational lens is a poor quality lens, but it is a lens. This is formed, you can form a gravitational lens by taking a wine glass and cutting it off and throwing away the top. Just keep the bottom stem of the wine glass that flares out to be the glass, the support of the glass, and pass it over. Now, in this case, the gravitational lens is made up and runs across this way. I'll show you what it does. It's sort of neat. Okay, So this guy, I don't know what this is, I think Seattle. The gravitational lens is coming in, and this material is getting, whoa, it's getting bent by the wine glass or gravitational lens. You see, everything is bent. It's bent around it. So if you ever see Seattle or some city looking like that, at least you know what it is. Okay? Gravitational lens passing in front of it. And that's how it works. That's a simulation of the gravitational lensing process. In the reality, in order to bend it hard, to really bend the light, you have to have a lot of mass. And the mass needs to be, it cannot be the mass that you can see in the galaxies. In order to bend the light, the mass has to be in the form of apparently something else. And that something else is apparently dark matter. It's dark matter because we can't see it. So, I mean, that's a reasonable name for this. It's dark matter. You know, we don't know what it is, but you can't see it. By the way, there is an experiment ongoing to try to identify the dark matter. And this is happening at Berkeley. Bernard Saddeley he's been trying to find dark matter for 20 years, 15 years, and he hasn't found it yet, but he's looking with particle techniques, and we'll talk about that. Now, the question is, what is the dark matter? Here's our galaxy, and to recall that the rotation curve of the galaxy went up and stayed flat. It didn't go down to zero. These rotation curves were a tremendous mystery when they were first seen, but the atomic clock, most of the galaxy is stars down in the center of the galaxy. And there are two possibilities for why the rotation curve climbs and then stays up, it doesn't go down. Two possibilities only. And the possibilities are that we don't understand gravity on this scale. We've made a mistake. Kepler is wrong. Newtonian mechanics does not work on this scale. Or the hydrogen velocities we measure is by the gravitational attraction of this stuff, dark matter. And the scientists universally, almost universally, think it's number two. That is what explains it. If we trust the theory of gravity, there's a lot of dark matter, 10 times more. The galaxies, the luminous matter is confined to a disk. The dark matter is not confined to a disk. It's in a sphere around the galaxy. It's found in a halo and far beyond the luminous disk. This is understood. Scientists understand why the baryonic, the ordinary matter, is more centrally condensed. It has to do with the fact that the ordinary matter can suffer collisions. The collisions heat up the gas, and the gas radiates the energy away, and then it sinks. It sinks, and the dark matter can't do that. There's no way for it to sink, because it cannot suffer these collisions. Okay, now let's do this again. Come on. Okay, we did this experiment already. Let's remind you. If we're going to measure the rotation curve along points along this galaxy, which is possible to do. It's easy to do this now with modern instruments. So you first get a redshift, a blue shift here. If you go away from the nucleus, you get You get a redshift over here, over here, over here, over here. Now we're going outside the galaxy you can see, but it is possible to measure it in terms of gas, which is associated with the galaxy. Rotation. And if you go on this side of it, you see, all right, so the rotation curve, all right, the rotation curve comes up and then down and up. All right, now if you look at these rotation curves, okay, so you construct the rotation curve and you see a figure like that all the time. Okay, the rotation curve of a bunch of galaxies, just any bunch grabbed at random, looks like this. Now this is one rotation curve. It's not two of them. I folded it about the center, and the rotation shows it climbs and goes like this. And as a function of distance from the center, in thousands of light years, it does that. And we expected the dark matter, if it were no dark matter, the galaxy would have done this. But it doesn't. It stays high. Okay, they are flat to large distances, and it tells us that the dark matter, if we want to interpret it that way, is distributed outside the disk. You can measure dark matter in elliptical galaxies. Let me skip that. But ellipticals also show this dark matter. All right, so the mass of a galaxy, just for convenience, it's possible we talk about something called mass to light ratio. And it's measured in solar units. Mass of the sun divided by luminosity of the sun. You express it in solar units. And this takes mass to light of the sun is 1 by definition. All right. But within the orbit of the sun, the mass to light ratio for the galaxy is 6. Now, it's 6 because the galaxy is not dominated by stars just like the sun. It's dominated by faint stars. The faint stars have a lot of mass. They don't have much light. And that is consistent with the dark matter being dominated by, not. That is consistent with the starlight. All right? So inner regions, you see, in elliptical galaxies, you see somewhat higher value. You get a value of 10. All right? But if you include the outer regions, the entire galaxy might be 50. Dwarf galaxies can be higher. And most of the matter is not stars. And this tells you if it's 50 and you compare to 6, it tells you that the object is about 9 times more massive than indicated by the starlight. All right. So that is very strange, but that is real on every object. What's the dark matter made of? Fundamental question. What is it made of? Okay, now, what could it be made of? It could be made out of protons, neutrons, and electrons, the ingredients of ordinary matter. Is that a possibility for the dark matter? All right. Why is it not visible? If it's ordinary, it might be out of the same stuff we're made of, but then it doesn't shine. Why doesn't it shine? It's dim, incredibly dim. All right, if we've not discovered it yet, which is the case, if the dark matter is some form that we don't really know, we call it extraordinary dark matter, extraordinary matter. So we don't know what it is, just give it a name, extraordinary. That's the name of it. Okay, what is this stuff? And what physicists, we call the ordinary matter, neutrons, protons, and electrons, is called baryonic matter. Neutrons and protons are baryons. It's a term used in particle physics. The way to say it is the extraordinary matter is non-baryonic. One way you know it's non-baryonic is that the bullet cluster indicates that the dark matter collided, or did not collide with itself. It just went through it. If that were made of matter of neutrons and protons, it would have collided, and you see nothing like, you never see the bullet cluster or other things. We're pretty sure that the dark matter is not made of baryonic matter. Okay, so what is this stuff? All right, we studied one non-baryonic form of this stuff, and the form it took was neutrinos. Neutrinos detected coming from the sun. We know neutrinos exist. Can neutrinos be the dark matter? And the answer is no. They interact with ordinary matter through two processes. They interact by gravity, and they interact by weak force. Remember, weak force, strong force, electromagnetic, and gravity are the four forces. The weak force is specialized to neutrinos. The weak force is something that protons and neutrons also, suffer it, but it's very, very weak. Weak enough that the particles don't really collide under the weak force. So we say that they are weakly interacting. The neutrino is weakly interacting for that reason. And their masses are low, speed so high, they'll escape gravitational pull of a galaxy. They can't be the dark matter. Now, long time ago, we did simulations of this, and our simulations said dark matter cannot be neutrinos. This was 30 years ago we published this. This is what we thought might be the dark matter. The Russian school thought it was the dark matter, but they gave up on that. This was the first candidate to be the dark matter, and it was wrong. All right, so what we want is a massive weakly interacting particle. Weak in that it doesn't suffer collisions that you can see. All right, it doesn't, never shines luminous light. And this weakly interacting particle is known as a weakly interacting massive particle, or WIMP. That is the dark matter candidate, WIMPs. So if you say that's a wimpy particle, but it is the weakly interacting massive particle. Or that is the name of it. It's pretty silly. All right, the particles are theoretical. They've not yet been discovered. There's plenty of reason theoretically to believe they're there, but and the idea is they'd be massive enough to exert gravitational influence. They're much more massive than a neutrino, and if they're weakly interacting, they don't emit light. If there's no light, you won't. It's pretty hard to see it. They have no charged particles, no charged matter in the whole business. Okay, and weakly interacting particles would not collapse with a galaxy's disk, and they are a natural candidate to be the dark matter around a halo. So that's why we think they're weakly interacting. Okay, so they're gravitationally bound to the halo of the galaxy, and now we've been talking about the galaxy formation. Galaxies form by the gravitational attraction of little points, and the points had high gravity, attracted each other, and made galaxy. You can ask the same question. What about the matter distributed on larger scales, which is so inhomogeneous? That matter should attract other matter, and that should give rise to something you can see. And here is a simulation. This is something I did. This shows this is about 50 megaparsecs across there. It's much bigger than a galaxy, measured in 1 megaparsec scale. This shows the velocity of these, just a rough guide of the velocity of dark matter that's flowing to this wall and flowing to a high density region. This is something you can measure locally, and this is work I've done. You can read about it, but look up my papers, but I don't really recommend that. All right, this gravitational attraction has overcome the Hubble expansion if they're on close scales. Otherwise, it hasn't yet. It has something known as a peculiar velocity, and that's what's drawn here. The peculiar velocity is a velocity that differs from the Hubble flow. We see a galaxy at a velocity. We don't really know that the velocity is purely Hubble flow. It could be Hubble flow plus a peculiar velocity generated by the attraction of everything. Our velocity, relative to frame, I'll tell you later, is 600 kilometers a second. How did that get generated? 600 kilometers a second has to be explained by something. And that is explained by peculiar velocities, something of this sort, that maybe we'll talk about later in the course. Now, this can be measured out to considerable distance. It's done. I'm going, at the end of the course, when we have a final exam, I'll be on my way to Israel for 2 weeks. The GSIs will take care of the exam. And there's going to be a conference talking about this sort of motions, about which I have a speech, et cetera, et cetera. Okay. The structure, everything in the universe shows the initial structure of the universe. If the universe is dead smooth everywhere, then there's no way, there's nothing to attract other matter. It'll expand, 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 and nothing attracts it, and it just stays there. The universe had fluctuations in its beginning. Why it had fluctuations, we'll discuss later. But these fluctuations were responsible for the growth of all the structure on smaller scales. It made the galaxies, the clusters of galaxies, etc., etc. And this is an important diagnostic of the universe. It's really quite incredible this is all doable. So it is these overdensities turn out to form all the structure we see. They've been growing since the universe was very small. And we'll talk about how they got there and what they mean. It is bizarre. Okay. And all these collapses don't work unless there's a lot of mass associated with them, and that mass is all associated with the dark matter. Okay, now there's something we call the critical density. How strong must gravity be to stop the entire universe from expanding? The universe expands, 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 and meanwhile, the galaxy, or the mass in one part is slowing it down. It's attracting itself to each other. And eventually it attracts, and then it turns around. It can expand, 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 and then collapses, and then collapses down to a point. All right, so we don't really know what's going to happen. And how can you study this? All right, we talked to this is called the critical density. If the mass of the universe, if the density of the universe is low, then it doesn't have any trouble expanding forever. If the mass density is high, it will turn around and collapse. And we say if the mass has exactly the critical density, it expands, 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 slowing down, but never really turns around. That is a critical universe. Now, we thought the universe is critical. That was the thought 20 years ago. Everybody thought the universe is critical because that's the simplest universe to describe, among other reasons. We thought it was critical, but it's not. It is crazy. Now, the value of H naught tells us the kinetic energy. The critical density is 10 to the minus 29th gram per cubic centimeter. Now, grams per cubic centimeter. What's the mass of an atom? One atom, say of hydrogen? Anybody know? Avogadro's number? All right, the mass of a hydrogen atom is 2 or something times 10 to the minus 24th grams. So that would mean if you have one hydrogen atom distributed in 10 to the 5th, a volume of 10 to the 5th centimeters cubed, that's enough to close the universe. Now that's not very high density, right? That's a hell of a vacuum. A perfect vacuum. You can't get anywhere near that in a vacuum system we build on Earth. Yet, it is enough to stop the universe and turn it around and eventually collapse it. So I'm not talking about ordinary times. This is really exotic. All right. Now, in terms of mass to light ratio, the average mass to light ratio has to be 1,000 times the mass to light of the sun. And we don't see any systems that have 1,000. The most we see is a few hundred. We don't have enough mass. Apparently, we do not have enough mass to make the critical density. And it suggests the universe is going to expand forever. 13.3 or whatever billion years old, but it's going to keep going. Someday it'll be 100 billion years old. You'll have long beards, you know. Old, old, old. All right? So that is crazy. Now, is that right? Okay, but there's something else. This is a mind-blowing experiment discovered just 12 years ago, 1998. Okay, what they saw is the following. The critical universe is the blue line, like this. Here is now, and this would be the future. If we have enough matter to overcompensate, the universe starts off at a beginning, goes up, and then collapses. And that is thought of, you can think of that as the trajectory of a balloon. Starts off at a point, it expands, and then collapses. And that is what happened. But that doesn't fit the data. If the universe is let's see. Critical, okay, yeah. All right, I'm sorry. The critical density is not the blue one. It's this one, the yellow, the greenish one. What is that? Yellow. All right, that has just enough matter for the universe to expand and then stop. And that doesn't fit the data very well either, particularly high redshift. Now this is looking back in the past, looking back 4 billion, 8 billion years. You look back 8 billion years, the time travel is large enough, and you look at it. Now here's one here, coasting. This one has, it's basically a universe with nothing in it. It just flows away. Okay, and that doesn't fit the data either. Coasting, a universe with nothing in it, is not sufficient to fit the data. Instead, the universe is accelerating. In other words, If I throw a ball up in the air, it doesn't fall back. It takes off. I just threw it, and then bang, takes off. That's what the universe is doing. What the hell kind of universe is that? All right, that is discovered in the last 12 years. We thought it was doing that before. There's lots of evidence that it was. But this is direct observations of these objects. And this is worthy of Nobel Prize, and they won a Nobel Prize this year. Saul Perlmutter and Adam Rees and oh God, a guy from Australia. Anyhow, these guys were head of big teams. It's not really fair to give it only to them, but they decided they can only give a Nobel Prize among 3. They can't give it among 20. So 20 people really worked on it, and this is the result. The universe is accelerating, and that is so bizarre. If you put matter in the universe, ordinary matter, it doesn't accelerate. There's no way to make ordinary matter accelerate. And baryonic matter, or dark matter, doesn't make the universe accelerate. It's crazy. And so you want to understand how you can get such an insane, how it can act in such an insane way. This was done with these white dwarf supernovae that we were talking about earlier. The white dwarf supernovae are great ways to see this. Okay, they're a great standard candle, and they're fainter than predicted, and they are interpreted as being accelerating away from us. Okay, the galaxies should be closer. Supernovae are further back in time. So this is the most bizarre type of result. Okay, the universe is accelerating, and there is an unknown force that is known not as dark matter. Be careful here now. It's known as dark energy. It's not dark matter. It's completely different than dark matter. And the distinction is important. And we'll talk about how you get dark energy. Believe me, you don't get it in a laboratory. Okay. All right. Let me show you a couple of come on. Here it is. Okay. All right, now, let's look at this universe. We're going to play with the universe, and we're going to play with its density. So first, let's make the density low. Okay. Say 0.5. Oh, I see. I do it this way. Okay. All right, so density is low. All right, and here's the co-moving grid. And start the universe. Now here is a drawing that shows what the universe is doing, and it's basically expanding, expanding, and it expands forever, and that doesn't turn around. That's a low density. All right, let's raise the density. All right? It's curving, and it looks like it has enough matter to make the universe turn around. All right? So if we make the matter, if we make the mass higher, then do it again. It doesn't get very far until it collapses. Okay? So the universe will not get far if the density is too high. If the density is too low, the universe escapes. It escapes itself. All right, so this is the role of the density parameter that you play with, just like this. This is a nice way to see what the universe is doing. Yeah?
So if it does collapse into itself, is that just kind of like a cycle where it collapses and Big Bang goes again, Big Bang?
Oh, maybe. It could. Yeah, that's an idea. That certainly was an idea that was relevant. I mean, that was a conversation of what happened. People had no idea what was what. But we don't think that's the answer now. Okay, the new data is very, very different. All right, so let's take a look at this. Okay, now we have there's two dials now. There's the dark matter, and there is the dark energy. Strength of the dark energy, okay? The strength of dark matter. So let me tune this down. Okay, let's try this and have no dark energy. And the universe just expands, all right? Let's tune it up. Tune it up, say, to a high value. Well, this universe really wants to expand. All right, the universe, this one apparently is just massive enough to turn around. Okay? Now, let's put some dark energy into it as well. We'll put in some dark energy. The universe doesn't really respond for a while, but oops, it's taking off. The universe is accelerating now. Acceleration is when the curve turns up. You all took calculus enough to know the difference, right? Deceleration is when it turns down. But acceleration is what the universe does. Note how convenient it is to plot everything in terms of this parameter that measures the size of the balloon. We're going to use this again. So everything is cast in terms of the radius of the balloon that we're living on. Okay, so now let's put get it up a ways. All right, and begin. And the dark matter turns it down, and whoops, it inflects once. Here it's decelerating, here it's accelerating. The universe started off decelerating, but later the dark energy caused it to accelerate. Now what is happening is the dark energy is something called a vacuum energy. We'll talk about how that works. And the vacuum energy does not dilute as the universe expands. So you start off with the universe of a size, and it has a lot of matter in it. It's dense matter, has a lot of gravity, but the universe expands, the matter dilutes. But the dark energy does not dilute. Craziest thing, the dark energy is the same. How can that be? If I just expanded the balloon and dark energy expanded? All right. Now, the trouble is, I can't use math for this course. In mathematics, it's very simple to explain this. That's God's language, but we have to use old-fashioned English. And that makes it hard to understand. All right, so the universe manages to expand in this case. All right, so that is really, really bizarre. Okay, now let me just finish the slides. Okay, the idea is we have 4 universes to choose from. We have the universe started as a Big Bang down somewhere. And the present is right here. The future is this way. Past is down here. The universe started, it could have been a recollapsing universe, first one. It started and expanded, then collapsed. That was one idea. The next idea was a critical universe. It expands, and it slows down as it expands, and eventually slows down. But if you lower the density a little bit, it'll go into a coasting universe, where the mass has escaped itself, the velocity is higher than the mass can retard, and eventually just flies away. Meanwhile, an accelerating universe grows, and right away, in the future, it's going to expand faster. It's not going to slow down. It's going to be very, very fast. Okay? That is what apparently our universe will do. And that's different from any of these other universes. Unfortunately, we cannot, in such a universe, you don't get a chance to repeat it. You have one shot. Okay, and apparently the one shot is led to the accelerating universe. So that's new data. Nobody was thinking of that, but that's the way it goes. The critical density won't collapse, expands slowly. Coasting universe, and the accelerating universe, it accelerates, and that's the model that currently is favored. All these models are consistent with Einstein's theory of general relativity. All of them. Einstein's theory does not pick out our universe. It just has a mathematical framework to allow the description of any universe. It's very easy, actually, to play with Einstein's equations and to turn them and to show what these different universes do. It's no problem. If you would take this, if you are a student in the astrophysics department, you would study how this works by the time you're a senior. Okay, it's not a difficulty. Okay, so now here I want to show you this. This is a super simulation run at Max Planck by Simon White. He used to be here. This is why I came to Berkeley. He was here. And this simulation shows us going into it, 250 megaparsecs. It's a gigantic job. This is a huge job. It used every computer in a supercluster. This is in Munich. This is showing a rich cluster of galaxies in the simulation. Filaments and voids all over the place. An amazing picture. Oh, God, we're out of time. I'm sorry. I will show you the remaining movie next time. Okay. All right, that's how our universe is made. That is the work I have done. I didn't do all this work, but that's my field is in this field. And it's been an incredibly exciting time to be in it. All this is new. None of this was known when I started this school. In fact, I started large-scale structure. Nobody before me had the patience to look at these galaxies one at a time. So all this has incredible progress. Incredible. Okay.